Please join me in welcoming Dr. J. David Rogers, who is our keynote speaker for today. Dr. Rogers holds the Carl F. Hasselman Chair in Geological Engineering at Missouri University of Science and Technology in Rolla. He received his BS in Geology from Cal Poly Pomona. He's a West Covina native, yes? Yeah, he's one of us. An MS in Civil Engineering from UC Berkeley, and his doctorate also there in Geological and Geotechnical Engineering. 25 years he owned consulting engineering and construction management firms with offices in San Francisco, Los Angeles, and Honolulu. He served on the Berkeley Faculty of Civil Engineering for 7 years prior to accepting his current academic position in 2001. He recently completed a book on the engineers who built the Panama Canal, and anybody ever seen the photographs he's got of the Panama Canal? They're extraordinary. It's a really interesting project. The book was written to commemorate the canal's 100th anniversary. Rogers has published over 100 papers in refereed journals and conference proceedings, including award-winning articles on geoforensic evaluations of dams and levee failures, as well as various aspects of civil engineering history, such as the St. Francis Dam, the Hoover Dam, the Miami Conservation District, Tennessee Valley Authority, the Mississippi River and Tributaries Project, flood protection of New Orleans, environmental security in the Middle East, and the Panama Canal. That's quite a remarkable body of work. His passion is the evolution of geotechnical engineering and engineering geology in practice, which is covered on his website through Missouri Science and Tech. Please join me, folks, in welcoming Dr. J. David Rogers.
This here?
Yeah.
Please. Okay.
We don't have a spare laser point in them, do you? Just asking.
All right. Well, let's get going here with it, see if this works. Just a colorized image by Pony Horton. Pony did about 7 photographs for me that he colorized years ago, which were very, very valuable, especially in discerning silt from sand and things like that. St. Francis Dam was 205 feet high. That was big for that era. It was one of only 2 concrete dams built by the city's Department of Water and Power. They were actually called the Bureau of Waterworks and Supply at that time. They became DWP in July 1931 after the failure. It failed catastrophically, as you've heard, killed at least, I guess it's 431 now, not 432 people. It was the worst American civil engineering failure of the 20th century, and it had huge ramifications in California and in Washington as well, including requiring professional engineering registration of civil engineers in the state of California. The guy that built it headed up the water department for many, many years was Big Bill Mulholland, who had left Northern Ireland at the tender age of 14 and made his way eventually to California in 1877. Took a job as a ditch tender at Zanjero for the Los Angeles Water Company, adjacent to the Los Angeles River, around 1879. And he became the chief of that water company, succeeding Fred Eaton, when Fred Eaton became the city engineer in 1886. And it was bought out by the city in 1902. And there were no records. The records were all in Mulholland's brain. And so they got a board of public service commissioners, and they went down and sat down with Mulholland for a couple of weeks, and he drew a map of the whole town and said, you got 5-inch lines here, 4-inch lines here, 2-inch lines there. He had it all in his memory. He was the principal visionary of the first Los Angeles aqueduct, which was I can't underscore what kind of precedent-setting project that was. It was the first time and only time in world history that a municipality built a water supply system ahead of its population. It almost always occurs the other way around. You wait till everybody's starving for water, then you have a referendum, then you go build the Croton Aqueduct like City of New York did in 1832. And they did it again in 1893, and they did it again in 1917, and again in 1935. They just kept, they always were building the water infrastructure behind the burgeoning population. He solved all kinds of incredible problems to bring that project in on time and on budget. He was a born problem solver. What was his Achilles heel? There were several. One, he never had formal schooling, so that dart was always thrown at him. Don't let that bother you if you're one of those people. because the smartest people I ever met were house movers, and very few of them ever went to college, but they were sure smarter than I am with all the stuff behind my name. So I have a lot of respect for Bill Mulholland. I want you to know that up front. There was a water crisis. Instead of the water was supposed to last for 50 to 75 years, and they were letting ranchers in San Fernando Valley buy water so they could ranch, and of course that increased the value of their land. The value of land in Southern California is tied to the availability of water. If you can get water, the land's valuable. If you can't get water, it's not worth nearly as much. And so they had a drought. And while the aqueduct was under construction, look up there, the city's population from 1906 to 1913 doubled, nearly doubled. And from there to 1930, it tripled again. And then in 1930s, you actually went from 1.21 million people up a little over 3 million people. So LA had incredible growth in the 20th century, especially post-1945. They had near record low rainfall, so they ran out of water and in the early 1920s. So for a waterworks engineer like Mulholland, if you're running out of water, the thing to do is to build more reservoirs, so you don't waste any water out into the ocean. That's the way engineers saw the world. Now, civil engineers, waterworks engineers of that era, were the rock stars of that era. West of the 100th meridian, they made it possible for people to live and to cultivate food. And the guys that brought along refrigeration, air conditioning in the mid-30s were the other pariahs. Because without air conditioning and without aqueducts, we don't live here. You can only support 250,000 people in the city of Los Angeles with the indigenous water supply of the Los Angeles River. Okay, prior to 1923, all the dams he had built, which is about 20 of them, had been earth-filled dams. And Weed Canyon, which is right opposite Hollywood Bowl on the other side of Cahuenga Pass, looking north, was their first concrete dam. And the reason was there wasn't the earthen material there to make the impermeable puddled core to do an earth fill. So they built a concrete dam that was just about 200 feet high, so a little under. And when it was christened in mid-1925, they named it Mulholland Dam after William Mulholland. It's always been Hollywood Reservoir and Mulholland Dam from day one. Still is today, believe it or not. So that gave them the precedent of doing a concrete gravity arch dam. Mulholland remembers when they were building the aqueduct through San Francisco Canyon. And San Francisco Canyon is very famous in Southern California history because it's one of the only natural passes that allowed the stagecoaches and horses and everybody to come in to Los Angeles from the north. So it was a regular stage route that ran along there through the canyon. It's on all the original railroad surveys in the early 1850s. And they put the aqueduct through there in 1911 in a series of 9 miles of tunnels, 6.5 miles of tunnels over a 9-mile stretch. And he tried to build the dam originally in Big Tahunga Canyon. The guys that owned the ranch land out there saw the city surveyors, and they held out for a high price because they're going to sell to the city. And Mulholland was a skinflint. He didn't want to pay anybody 1 penny more for being speculators. He didn't like speculators. Politically, he was a progressive, no question about that. He did not like politicians because he said, politicians lie. If I became a politician, I'd have to remember what I said, because if you lie, you have to remember what you said. And once he was actually voted the most popular person in the city of Los Angeles many times by whole uproar. They tried to draft him to run for mayor. And here's what he said about being mayor of Los Angeles. He said, I'd rather give birth to a porcupine backwards than to be mayor of Los Angeles. Is this my kind of guy or what? I like this guy. All right. Construction of the St. Francis Dam began in mid-1924. And they built a cutoff wall, a little coffer dam. It was only 8 feet high because there's not much water in that channel in the middle of the summer. And that shows outlet number 1. You see outlet pipe number 1, which is 2 steps above the bottom step. That's going to figure real important later when we do the forensic analysis. When you do forensic analyses, what you go after are photographs. Photographs are the most reliable documentary source out there until we got all the computer ways of altering photographs that we have now. But in the old days, you know, photographs were better than people's memories. You never have too many photographs, especially aerial photographs. And so they started placing concrete. And in the 1920s, there was a lot of problem with the ways they placed mass concrete. You see here is a bunch of billowy pillows. They're not trying to set the concrete into casements so that you can have contraction joints like you see in Hoover Dam, where they were typically 50 by 50 casements, and you'd only pour 1 foot of concrete at a time. And what they did here, they brought the concrete down in troughs, and they just, pushed it out there all over the place, and you had little ponds that would form on top, and you get that real soupy latence layer, which becomes a low strength layer. It's high water cement ratio. It's very, very porous, and it's not a good thing for dams. But all the dams, built up near Santa Barbara, up the coast, down here in Southern California, up through about 1930, have that problem. And a lot of them, most of them, have been retrofitted since they were built. They had minimal excavation of the abutments. The left abutment was in Pelona schist, right along foliation plains, which are weakness plains in the mica. You can see it dipping down about 35 degrees. They're only excavating about 7 to 15 feet into that material, which isn't very deep for a 205-foot high dam, but that's what they did on the left abutment. And on the right abutment, they were in conglomerate, and they put a trench in there with a steam shovel. This is the view looking upstream during construction. Those big towers are what they lifted the concrete from the batch plant at the bottom, right at the bottom of the base of the dam was a concrete batch plant. They then would lift the concrete up, and then they'd have it go down these troughs, just like the ready mix, the troughs you see on the back of ready mix trucks, except these things are 400 or 500 feet long, a couple hundred feet long. And what happened is you get aggregate segregation when you put concrete down a trough. It's the same problem they had with Gibraltar Dam up on north of Santa Barbara. It was built in 1925. So they weren't doing concrete placement the same way 10 years later. That was something they didn't understand. What was good about this dam is that it had a step face, and that each one of those steps had a different width depending on its elevation. The steps varied from 5.5 feet down at the lowest elevations of the dam, and they narrowed to as much as 1.45 feet up near the top of the dam. That figured very prominently in the forensic assessments they did later to tell where the blocks came from in the dam up to a mile downstream. It was completed in May 1926, so in 22 months, 130,000 cubic yards of concrete, 11 little spillway panels you see up there with the sky just peeking through them. They were only 18 inches high. We've never, ever tried to do a stunt like that today. 18 inches high means any tree that comes down there is going to get caught in it. So that's not a lot of freeboard, but that's what they did because they didn't expect this thing to ever be spilling because it's an artificial, it's an aqueduct dam. It's not, it's designed to catch water from an aqueduct. It's way larger a dam than you'd ever build in San Francisco Canyon for the amount of water you expect to collect in San Francisco Canyon because it's pretty dry in the Sierra Pelona. It had 5 30-inch diameter outlet pipes with a maximum capacity of 1,184 cubic feet per second if you had a full reservoir right to the spillway slits. If all 5 of those outlets had been opened at noon on Monday, March 12th, when they were out there inspecting the dam, Mulholland and his chief assistant, Harvey Van Norman, they would have dropped the reservoir by only 1 2/3 feet in the next 12 hours. So it wouldn't have, it's like, you remember the failure of Baldwin Hills, December 17th, 1963. It took them 5 hours to figure out how to drain the dam. They didn't have a plan for that, how to drain the reservoir. If they had had the plan in place, they could have saved it. But they didn't get that plan going, reversing the pumps and emptying it as fast as they could till 12:30, and it failed at 3:50. So that's why you want to have a plan. A plan so you don't waste time. What do I do? What do I do? What do I do? Here's what the plan says to do. Play it safe, drain it fast as you can. The reservoir was brought up to spillway level for the first time almost 2 years into its operation on Wednesday, March 7th, 1928. All the city reservoirs were full by the following Sunday, March 11th. And that's real important in the story, very important. So all the city's reservoirs were topped out. They could take no more water. So they began dumping water on the Drinkwater Canyon bypass. Well, the first time they'd ever used it was the day the dam failed. So all this water coming down San Francisco Creek that hadn't been coming down the creek the day of the failure. A lot of people who were local residents recall that and saying, the dam is leaking. No, the aqueduct was dumping because they couldn't store any more water, and it was cool and clammy and low ceiling, so people weren't using a lot of water. Dam keeper Tony Harnischweger called Mulholland that morning to report dirty water coming from the right abutment area. There's always water leaking out of dams. And there's always water leaking on the abutments of dams and underneath dams. That morning they had about 2 cubic feet per second spillage coming over the spillway panels, darkening the downstream face. That wasn't what Harnischweger called them about. Harnischweger's calling them about water that's coming out of the upper end over in the dike section and coming down, and it's muddy. And when a dam engineer gets told he has muddy water, that means you could have hydraulic piping, like underneath a levee. And you get very excited. You don't want to have muddy water. Clear water is fine. Muddy water, bad juju. Don't want that. And so Mulholland races out there. He doesn't drive. He has a chauffeur-driven limousine that takes him and Harvey Van Norman out there. When they get out there, and this is where there's a real unusual case. You can't find another dam failure where the chief engineer and the assistant chief engineer are there looking at it 12 hours before the failure, and what do? They bless it. It's like, everything's fine. See you later, alligator. Well, that's what they did. They came up there and looked at it, and he said, I don't see any problem, we got high water, and he found out that the leak, what happened is the leak was coming through as clear water, and then it came down a construction road they were just putting in, and it picked up the dirt when it went over the uncompacted fill on the shoulder of the road, and that's how it got muddy. So that was a reasonable conclusion to draw. I can't fault him on that one. I probably would have said the same thing. It went out in the middle of the night. And the first 62 victims were employees and their families of the Department of Water and Power, who lived just 1 3/8 miles downstream. Lots and lots of dead children. I'm very zealous about flood safety, and a lot of people call me up. I talk to the media all the time. And they say, why are you so zealous? So-and-so over at this university is not nearly as concerned as you are. And I said, the difference between him and me is I pick the dead babies out of the trees. You do that, you have PTSD. You don't get that out of your... There's a little boy about the same age as my little boy, never identified. Looks like a Latino boy down in Oxnard. Innocent victims of flooding. That's what we should never forget. You can't do things too safe when there are things that can kill children. Tidal wave of destruction went down, about 125 feet deep, going down the canyon, almost a mile downstream. It spilled over a natural saddle you see there on the right that's 120 feet above the channel. The average velocity was about 18 miles per hour, 26 feet per second. That's pretty hard to run from. The initial flooding reached the maximum depth at the dam site of 140 feet. It filled all of San Francisco Canyon. The dark blue is the lake before the flood. The light blue is the inundated area going downstream. You can see all the buildings right there. That was the houses across from Powerhouse 2 that all got taken out. Only 3 survivors there. Lillian Curtis Eilers and her son Danny, and Ray Rising, out of the 70-some people that were there. So there are 64 victims at Powerhouse 2, and that you can see the penstocks come down there where Powerhouse 2 had been. It had been, the aqueduct was completed in 1913. Powerhouse 2 was completed in 1920. It then came down and met the Santa Clara River, spread considerably, took out all of Castaic area, killed, again, a lot of families in there, and then went down to Kemp Siding over there on the far right and killed 84 of the 140 Southern Cal Edison workers that were in a workman's camp there. That was so close. They were calling them on the phone, and the night watchman answered the phone, and before they could tell them, get everybody out of there, the phone went dead. They were just seconds too late to save the people there. It finally reached the Pacific Ocean at Montalvo around 5:30 a.m. By that time, it's only moving 5 miles an hour, but it's 2 miles wide. You wouldn't think that would be capable of knocking bridges down. It knocked down the Coast Highway and it knocked down the Southern Pacific Main Line. They're both taken out right at the coast. That's a lot of water to suddenly put in, and what happens is you get back eddy scour on the downstream side of the pilings, of the vents. And the Santa Clara River is just pure sand, so if you put a lot of load on it, it's going to eat down. So if you have 5 feet going up, you're going to have about 15 feet of scour going down. And that was the problem. So it was a scour problem. Took out the bridges. There's a map of the flooded area. The narrow part is coming to 7 miles down San Francisco Canyon. Then it widens suddenly right about where Saugus is, and then out to the ocean. 52-mile path when you smooth it. 54 miles for the ocean, 2 miles shorter because the flood's just going cutting off the corners. This is an aerial oblique view taken by Floyd Spence the morning after the failure. As a geological engineer, first thing I notice when I look at this thing is the big abutment failure. We call that the left abutment. In dam and hydraulic engineering, we look downstream. This is the left side, that's the right side. So you look like the water going downstream. So the left abutment had a very large landslide. And that's the thing that's surprising right now. You see it truncated the road, took out about a quarter mile of the San Francisco Canyon Road. Mulholland and his assistant Harvey Van Norman had a hard time even getting there because the road up in the, and you'll see another picture of this in a minute, the road was taken out by other landslides. When you drain a reservoir very, very rapidly, you get something called a rapid drawdown condition. This is what kills levees. If you let the water go down real fast, you get an imbalance because the banks are saturated, so the banks just slumped into the reservoir. So they had to hike in, and the chauffeur had to dig steps for Mulholland, who's an old man, to get in there. You know, he's 73 years old when this happens. So between 40 and 80 vertical feet of the left abutment was eroded. So when you look over there and say where the landslide is on the right, the dam was built 40 to 80 feet above that surface. So it was an enormous amount of material that was eroded out of there. Governor Young appointed a 6-man panel to investigate the failure. That included 2 geologists. And they made a single visit to the site on Tuesday, March 20th. They depended entirely on information collected by others. And we can see the guy making a plane table survey over there on the right, which was the survey given to those guys. And the geologists in that group were very, very much impressed with this fault. You see right there, it looks like an interstate highway, that white line. The white contact with the gray is the fault. And here it is in black and white here. It's orange over silver. And they saw that fault and they go, who would be dumb enough to build a dam on a fault? That's what all my geology classes said at Cal Poly. They took us out there and they said, this is what happens with a dumb engineer who doesn't get geology and he builds a dam on a fault. Now, before you think Bill Mulholland's too dumb, he's the first civil engineer in the United States of America that recognizes faults and what risk they pose to water supply infrastructure. He wrote a whole paper about that in the Bulletin of the Seismological Society of America in 1918 and gave a keynote presentation at their annual meeting in Los Angeles that year. And he tells about intercepting the San Andreas Fault 400 feet below Lake Elizabeth when he's putting the aqueduct in. And he maps the zone. It's a zone about 300 feet wide. And that's why he wants to build a dam and a reservoir south of the fault to hold a 1-year supply of water, because if that fault moves again like it did in January 1857, Fort Tejon earthquake, it's going to take him a year to fix that tunnel. He was 75 years ahead of his time on that one. Now, that's all we've been doing, folks, for the last 25 years with all our water infrastructure in California, is trying to make it safe from seismic risk. So that panel concluded that there was hydraulic piping along the fault line that caused the material to slake. Now, the reason for this was when they took pieces, certain beds in the Vasquez conglomerate had gypsum in them. Gypsum causes clay to disperse. That means if I have some clay that has gypsum in it, and I put it in a beaker of water and I stir it up like a chocolate shake, it won't come out of suspension. It'll just stay in suspension. That's a dispersed structure. So when you see a pond, You drive by a pond on the side of the road, and it's still cloudy and muddy, chocolatey, 3 days after the rain, you got dispersive clays. That's the test for it. And so those are never good for hydraulic piping. Those are things that had materials that were subject to hydraulic piping. So they would take pieces of this conglomerate out, and they went into the coroner's inquest, and they put the conglomerate into beaker water, and the conglomerate just spontaneously disintegrated. They said, "Would you build a dam on that?" Well, the thing is, the dam weighs a lot. You put the dam on the material, it's not like the material can just disappear and come out of there. It has all to do with something we call restraint in solid mechanics. If it's restrained, the bad stuff can't hurt you. It's only when it's free to move somewhere that it can hurt you. So that's what they concluded at the time, and these guys got their report out first, so that's the report that's in all the textbooks to this day. That's how the St. Francis Dam failed. This is a colorized image that actually shows the fault. You can see that silvery material is the Pelona schist. The orange material is the Vasquez conglomerate. Now, when you're on any kind of forensic panel, and I do lots of these still right now, I have the Oso landslide in Washington I'm doing right now. It killed 47 people last year. I'm chairing that commission. You are always going to be taken hostage by things that are graphic. And that's good. You got to take them in, but you can't let them over-prejudice you about what's going on. Going out to the site one time, not making any independent measurements, these are all things you should not be doing in a forensic investigation. And you want to get people of different backgrounds, different experiences, as I'm going to talk about later. It's very important. All right, so here's the map that they were given, that the State Commission was given. Horace Wilde, who was a Division of Highway surveyor, put it together, and he shows the dam, and he shows block 16 way downstream of 11, 12, 13, 14, and 15. And block 16 came out of the left, or the right abutment side, right above the fault. So it's the block right up there near the fault. So that's part of why, again, that was circumstantial evidence. The panel said, well, that block went a half mile downstream, the other large blocks only went a quarter mile downstream, so it must have failed there first. They didn't have anybody in the panel, and they didn't have the expertise in those days with supercritical flow. Concepts of channel hydraulics hadn't been invented yet. So they were way, way off on the peak flow estimate. They estimated 400,000 CFS. When we did the reanalysis in the early 90s, we got 1.7 million. So you can see that's the kind of difference. We were off by a lot. Now, the other thing was a missing section. In the original state report, the yellow area was the area they hadn't identified any blocks coming from that area. And the white area underneath the left abutment is all the material that was eroded away by the outpouring floodwaters. And all of that is on the left abutment, not on the right abutment. It's like, do we have eyes? They did lose material on the right abutment too, but you can see nowhere near as much as was taken out on the left abutment. Big, big hole under the dam taken out on the left abutment. So that was the missing section. They fixed the blame and issued their report 5 days later. The team that gets their report out first is the team that makes it into all the newspapers. And after that, the story gets stale. Because that's what happened. And so that's the book that was put out, that's the story everybody tells. Now, one of the shortcomings of Wilde's plane table map was that it did not include the relative elevations of these dam blocks. Blocks 12 and 14 from the base of the left abutment are actually located 26 feet higher than block 16 way down there. And block 11 may have helped form a dam with blocks 12 and 13 that deflected subsequent flows off to the left, where block 16 was found further downstream. Now, if we go back, Charles Outland was a native of Santa Paula. He was a senior in high school, Santa Paula High School, when this flood came through his town and devastated his town. And he became an investigative journalist of sorts. He was a rancher by trade, and he did some great forensic work. So we don't have to go to college to get knowledge to do great forensics. What we got to do is just be careful and not be over-prejudiced. You know, collect all the information and look at it. And he looked at this construction photograph and he said, there's the lower outlet pipe number 1, and I count 1, 2 steps below that, and that's all. And he points this out in his book. First edition of his book comes out in 1963, second edition 1973. And when you look at that, what that tells you is this is the drawing that they gave to the state commission and said, that's the cross-section of the dam. Near as I can tell, all the part in yellow was never built. That was phony. That was not an accurate representation. You look at all the photographs, Outland's right. And that toe he shows, which is about 10 feet wide, I put in there in red. So if you look at where the outlet pipe was, that's what they actually built. When I got into the Bureau of Waterworks and Supply design files, there's the original design for the dam, showing a chopped toe very clearly. It did not flare out like it should have. It was a chopped toe, and they even put a shear key in. The worst possible place you could put a shear key in is the downstream toe. You want that shear key at the upstream toe, not at the downstream toe. But that's how they showed it. Now, also when you look at all the photographs, you see they didn't have the batter. There's a shifting batter right there, but they didn't have the bigger shifting batter down here to keep the toe out of tension. So that wasn't an accurate portrayal either.
Could you explain batter, please?
Batter is, let's go back. Oops.
And was this knowledge known at the time, or is it subsequent?
Would be about battering.
Well, the toe, you said, or not the toe, but the...
Well, it was a matter of it was good practice if you were at the top of the league in the Bureau of Reclamation, you would have known about that kind of stuff. But these weren't unusual kinds of things for the early 1920s. Because you didn't have a lot of dams out there. Elephant Butte was the best example that you had out there. There was a Bureau of Reclamation dam completed in 1915 on the Rio Grande. Batter is the part that is away from vertical. So the higher my dam, I have to keep the upstream heel out of tension when the water load gets all the way up the top of the dam. So what I do to help that is I batter the back of the dam backward to help keep that out of tension, so when this thing starts tilting and moving in cantilever action, that doesn't get a crack opening up. And that's exactly what did happen to the St. Francis Dam. It had a huge crack that opened up the upstream heel. We'll see that in a few minutes. There were also political promises that Mulholland made to the Board of Public Service Commissioners, where he said he wanted to store an entire year's supply of water. He said that in June of 1922. The problem was, every year, the city's consumption was going up markedly. So he changed the volume of the reservoir and upped it 2 years in a row. So he raised the dam 20 feet to get that additional storage, but he did not increase the base width at the same time. So the Stevens stage record measures how much the reservoir goes up and down. Of course, you have waves on the reservoir, so you can't just put a cork on the surface of the reservoir. What you do is you put a 12-inch diameter stilling well all the way down the base of the dam, and it has a 1-inch hole in the bottom of it. And so the water pressure is faithfully recorded inside that stilling well by a mechanical device on the top of the dam, and that takes away the wave stuff. You would be going up and down all the time. You're getting the mean hydraulic pressure against the dam. That was invented by a guy named John Stevens up in the state of Washington, and they're still used all over it. And they had to wind a device once a week with a brass key, and then they had a pencil thing that measured where the stage level was, and then you can see it starts to drop off about 3.5 hours before the dam fails. Then it goes down very suddenly. When you look at where the gauge is broken up there, it's broken like this to the left, suggesting the outflow is to the left, not to the right. That's an interesting piece of physical evidence. And then Carl Grunsky comes down from San Francisco. He works for the Santa Clarita Ranch Owners Association. They've hired him before to make critiques of the site because it was storing all the waters of San Francisco Creek, which recharged the Santa Clara River. And he won that particular litigation against Mulholland. He came down, and in the upstream heel, he finds the gauge attendant's ladder is crunched inside a huge tension crack at the base of the dam. Now, if I model that tension crack, it takes the resultant thrust of the dam out of the middle third of the dam, which it has to be for stability, and moves it 430 feet downstream. It's the most severe case of cantilever failure I've ever seen. So that is something you never want to see happen. But that explains the gauge dropping 3.25 inches over the previous 3.5 hours. It's just the tilting. It tilted 1/2 degree. And that's why it looked like the water level's going. The water wasn't getting down to Powerhouse 2. They didn't notice anything down there. If that was water escaping, they would have had a very significant flow downstream, more than 400 cubic feet per second. Okay. The main section of St. Francis Dam was built with 10 uplift relief wells. Uplift relief wells are just dry wells you put under the dam so that when the reservoir comes up and the water starts seeping underneath the dam, you drain that off and decant it to reduce the hydraulic uplift. The hydraulic uplift is equal to the reservoir depth. So if I have, 150-pound chunk of concrete and I put it in water, it weighs 150 minus 62.4 pounds per cubic foot. That's the weight of water it's displaced. So they didn't understand as well before this failure as they did afterwards was uplift is something you really want to do something about. And what he did here was very typical of the early and mid-20s, and that is to put uplift relief wells in, he had 10 of them, beneath the main section of the dam where you're going to have the greatest loads. And so that was a reasonable precaution. That was one of the good things they did do. They didn't have the uplift relief wells under the sloping abutments, but that was pretty common up until 1959 when Malpasset failed. So here's what that load does. The triangular load you see there is the water load against the dam when it's full, and then when you come underneath it at 2, 3, 4, and 1, that is the uplift load that's reduced by those wells being there. So he probably reduced it by 50%, but he still got a crack in the upstream heel, which moved R sub T, which is resultant thrust, outside the toe of the dam. That's why the big, huge crack is back there. And that was a 3.67-inch drop of the reservoir recorded 40 minutes before the failure. And so that explains why we see the record we do on the Stevens gauge. Now, when he was testifying at the coroner's inquest, he cited several books: Smith's Construction and Masonry Dams, Wegman's Design and Construction of Dams, 2 of them out of the 3. I went and got those books and looked at the design examples in there, and I could see that they had copied those. That's not hard to tell. And you can actually see, what the difference is between a dry dam and a dam where you're designing for uplift. And so that was there too. You can see that's why they put the uplift relief wells in. So here it's actually showing in one of those books, this is actually from Falwell's Water Supply Engineering. That's where the resultant thrust would be if it's absolutely dry, and there's where the resultant thrust would be if it's loaded with water all the way to the top. Now, I can't go farther this way than that point. That's the middle third. If it goes farther over here, you're going to be cantilever instability, you're going to tension back here at the heel. So you'd flare this thing out more, and that was the problem they had with adding 20 feet to the top and not adding any to the base. So cantilever action is just that. It's a cantilever, and you're pushing it over. And you're trying to keep the resultant in the middle third, and that is what's required for stability in cantilever action. Now, when we actually ran it on a computer, what we learn is the dam became unstable and overturning when the reservoir rose to within 7 feet of spillway crest. So adding the extra 20 feet on was very important, especially the last 10 feet was very important because it had the chopped toe. Now, arching, they did not design for arching at that time, but they knew it was a good thing to do, and so that was good practice. The fundamental theory for figuring arch stresses was developed in the mid-20s on a big multidisciplinary research project in California, actually, but the final reports didn't come out until this dam was built, 1926. So if we look at the arching loads, what we see on a computer, again using finite element modeling, we find out that when the water got up to 11 feet of crest, the arch loads suddenly got very, very high. And so it was not designed to incorporate the contribution of arching, but that would have been a problem for it when the water got that high. These are the reservoir stage curves for the 2 years of operation, 1926 versus 1927, and then almost 3 months into 1928. And what we're looking at here is the elevation of the reservoir in feet versus time, January through December. And we can see that in 1927, they got it to within 4 feet of the crest for about 5 days. So it got very close to what the load was that failed it. It got to spillway crest 7 days before the failure in 1928. So you ask yourself, well, what was so different between 1927 and 28? Those aren't very much difference. 4 feet. 4 feet 3 inches. 4 feet 6 difference. Not much. That bothered me for a long time. I didn't get that one figured out until this last year. In 1926, the reservoir was filled just 110 feet up to elevation 1780. There's what it looked like. Here's what the loading would have looked like. It shouldn't have had much problem taking that kind of. That's the kind of load, by the way, that Mulholland Dam has on it right now, up in the Hollywood Hills. It only has about that much load on it. The lake's more than 2/3 drawn down from its max capacity. January 5 to May 27, it was raised another 52 feet up to elevation 1832, spillways at 1835, so just 3 feet of the spillway, held there for 3 weeks, then drawn down to 1813 to 1819 until November 10. So why didn't the dam fail when you're that high? You're overstressing it for cantilever and for arching. Now, here's the important thing. During the first year of operation, several large tension cracks formed transverse to the dam's axis. These were likely in response to the cement's heat of hydration. When you have a lot of mass concrete, there's a chemical reaction that's occurring that produces heat. And that's why you get tension cracks, shrinkage cracks, and you get about 0.5% shrinkage. And so we build those joints into the dams, starting with Elephant Butte, 1915. But not everybody was doing that, but a few people were. And then you have to grout those. As the concrete cures, you then grout those openings. That's what they did at Hoover Dam. And so here they didn't do that. And after the failure, you can actually see stress radii in the face of the dam that actually show the crack there on the west side of Block 1 was a transverse shrinkage crack. It didn't go just straight through the dam. It went part way and then it jumped over and went part way again. So it wasn't just an open canal all the way through, but it was enough he's getting significant water flowing through it. And so if we look at where the cracks were, the 4 largest ones are shown in the drawing above. You can see that one on each side of Block 1, those were pre-existing shrinkage cracks that were in the dam. And then there was 2 real prominent angular ones at 3 and at 4 on both abutments, which is what you'd expect for not doing grouted contraction joints. This is some of the contraction joints after the failure that were photographed in the wing dike section. And they're about 3/4 of an inch wide, and these go all the way through because it's only a 20-foot wide section. And this is where the water was squirting through that Tony Harnischfeger called Mulholland about, was through the wing dike section. But you didn't have a lot of head there, so you didn't have anywhere near as much water coming through as you would have with the same aperture-sized crack in the main dam. So what did he do? He saw that in 1927, he was getting visible seepage, especially on the base of the left abutment of the main dam. And Mulholland, being a skinflint, and being that water's worth money in Los Angeles, he makes a big mistake, big technical error. And he didn't consult anybody probably. He decides to caulk the downstream face of those major cracks with oakum and to inject grout pipes and to try and grout the joints. You don't do that on the downstream face of a dam. You don't drive wrong way on an interstate, and you don't do this. If you're gonna seal those cracks, you gotta seal them on the upstream side. Because if you seal them on the downstream face, you're gonna get full hydrostatic force going into the interior of the dam, and it can't get out, and so it's gonna build up. You either give, pore pressure is not about the volume of water, it's about the pressure. It only takes, the crack can be as thin as a piece of paper, and it can cause a great dam to fail. So pore pressure is your enemy because it reduces friction and dead weight. And so that's what he did. And the reservoir was raised within 3 inches of the spillway on March 2nd. And I'm looking at different spots of the dam on the abutments as well as the main section. And the abutments don't have any uplift relief pressure. So they're going to get full reservoir uplift on all of them. And if we go and we look at where the seepage was, when he sealed it on the downstream face, that heavy black line there, you can actually see the crack when you look at the post-failure pictures. You'll see these dark areas that go up and then disappear. That whole dark area was an area that had water in it, which caused discoloring of the concrete. So you can see it didn't just go through cleanly. It probably came over, stepped over, and then went through the upstream face. You can see it in here as well, all the water coming out, dripping out after the failure. The concrete wasn't nearly as impervious as everyone had assumed. And this is the back of block 5 after the failure, and it's showing the back of this crack, and that's the oakum, that black stuff in there. That was a big crack. There's what the back of it looked like. It was huge. And these ripples you see on the concrete are where they place the concrete against the schist. So you're seeing the imprint of the schist structure, the foliation planes, just like a plaster cast of somebody's footprint. The 70 kV power line went down at 11:57.5 p.m. The Governor's Commission missed this because they got out there 7 days later. If you look at all the earliest pictures taken, you can actually see the downed lines in front of the dam. You see there on the left. And you look over here on the right, you can see the power line is up well above the high water line. And so, if you look at where the power poles were on the left abutment side, they're well above the dam level, actually almost 100 feet above the dam level. And so, you can't escape the conclusion, we know that power line went out at 11:57.5 p.m. We got that in all the SCE Saugus substation records. That's when the slide moved. That's how the line got taken down. The left abutment slide happened first, not last. That's a pretty easy one to sort out. So the east abutment landslide involved about 700,000 cubic yards of schist. It was removed in a very short period of time. The slide scar extended 130 feet above the reservoir water surface. We went out and mapped that landslide with a group from Cal Poly with plane table surveying in 1980. And then I got the city's engineering drawings and put the dam back in using one of the benchmarks they had put out there on the slopes. We were able to survey it in. And there you can see the gray outline of the dam, and then the brown is the landslide. Now what's bothersome about that is only 1/4 of the landslide had reservoir water against it. So how did this whole thing move if only 1/4? The red line is the fault over on the right abutment. There's what it looked like after the failure, about a 35-degree slope coming right down the foliation plains because they're made out of mica, schist, very slippery stuff. Oops, that didn't work. Okay, here's a block diagram looking at that slide. That slide that came out in 1928 is only a little sliver of a much larger landslide complex that was an ancient bedrock slide. And so it's a small piece of it that came out. You can see the power pole. There were 2 sets of power poles in the slide that got taken out with the slide. And that's why the wires were there on the downstream side of the dam. Stanford geology professor Bailey Willis was one of the first, probably the first cross-trained engineering geologist in the United States, and for many, many years, the president of the Seismological Society of America. He correctly deduced what was going on at the time, that the mass that was carried away was a small percentage of a much larger landslide feature, because he saw the B Highline Road had settled 9 feet, way up above the dam site, 180 feet above the dam site. So the whole left abutment had moved. And Willis was the persona non grata in Los Angeles throughout the 1920s, because in 1925, he had predicted that LA would have a huge earthquake after the earthquake in June of 25 in Santa Barbara. And the Eastern establishment quit insuring and quit making loans to Los Angeles construction concerns. He became public enemy #1 of the Chamber of Commerce. And so they went and got the geology profs at Caltech and asked them to write a refutation, and they wouldn't do it. They said, no, he's actually right. He's playing out. And so they told them, well, you shut up. You quit talking to the press. If you talk to the press, bad things will happen. They shut up. They were muzzled. And they brought in a retired USGS geologist named Robert T. Hill from Dallas, Texas. And he wrote a whole book, which came out in March 1928, about 3 days after the dam failed. And that whole book is a recitation telling you that there's no seismic threat to Southern California at all. Okay? He's a scientist, he has a PhD. And he's looked at it very carefully, and we had a big earthquake in 1857, and the next one shouldn't occur for thousands of years. And guess what? It did the trick. And Hill becomes a consultant to the Metropolitan Water District, to LA Department of Water and Power, of course, because what is he doing? He's telling the client things they like to hear. Interesting. So nobody listened down here to Bailey Willis, because Bailey Willis, was on the blacklist. When you look at the site, which I didn't, the first 20 years I was out there, I didn't see the big landslides. I didn't know about Willis's stuff. It was in Western Construction News. It wasn't a journal, you read a lot of. And I looked over at the benches, and I just went, wow, look at that bench. It's like an aircraft carrier. You don't get flat benches like that in the mountains without a good geological reason. Right, Larry?
That's right.
It's got to be a reason. It's a fault, it's a fold, it's a lithology change, rock type change, or it's a landslide. It's going to be one of those four, most likely. Site of an ancient Indian interstate highway or something. That ain't, something's happened there to have that kind of a bench out over there. That's the dam right there. All right, so we started mapping landslides. And lo and behold, they're all over the place. Big, large, rotational slump slides probably occurred during the last 100,000 years or so. And if we look at those, the dam site was an ancient landslide dam site. That's why the canyon was so constricted and closed. And that's why it was such a favorable place to put a lake. The ancient landslide lake was much larger than the St. Francis Reservoir. It was a much bigger slide. It was probably about 350 feet high instead of 200 feet high. But that's why it made a real favorable place to put a dam. It was a former dam site, a natural landslide dam site. The city didn't have to put out a report in 7 days. They sent people out there, Ralph Proctor, H.C. Gardet, and A.R. Arledge, and they made the best forensic, careful surveys of the displaced blocks. Yes, the city engineers did. And they put this out for their expert, Charles Lee, who they were using in the defense of their cases. I found it in the Lee collection at the University of California Water Resources Archives. And they identified the source locations of 17 of the blocks, many of them far downstream. They had 2 candidates for Block 35. Both were far downstream. Block 35 was the base of the missing section. It's the key block. And they identified block 32, the upper half of the missing section. There's block 35 over there, which is the furthest one downstream that you can identify where it came from in the dam. The base of the left abutment, not over the fault on the right abutment. So back, I remember I think AutoCAD 13 came out in 1991. I got so excited because now I could do three-dimensional puzzles. And I could start to put the blocks back together. And this was the first paper I ever published in 1992. It was all done with computer. It was all done with CAD work. And we were able to put the jigsaw puzzle back together. And then I started working on the abutment, on the landslide. And I treated it just like a dam consultation that I would today. So I went up there in the mid-'80s with Mike Scullin, who was an engineering geologist down here, one of the deans of engineering geology. He lived in Moore Park. He'd put me up for free. We'd go out there on the weekends and just collect data and rattlesnakes. There are so many rattlesnakes here. If you go out there, take an attorney with you. That professional courtesy, yeah, they don't bite you. Key block theory. One of the new things that came out at Cal Berkeley in the late mid-'80s was key block theory from Shi Genhua and Richard Goodman. And I had introduced those two men to each other. So I was really keen on using this. It was very useful to us on assessments of existing arch dams and gravity dams for the Bureau of Reclamation. And I ended up identifying 3 different wedges in the left abutment at the base of the dam that were troubling. A lot of other ones weren't troubling. These 3 were, because even when you put the dead weight of the dam on top of them, they moved. They came out and they lifted the dam up. So here's a discontinuous deformation analysis run where we're modeling the dam, the left abutment, upper left abutment, block 7. We got these rock wedges. We turn the water on and the wedges start coming out just downstream of block 35. That's interesting. Now, you don't stop there. So now I've got 2 failure modes, 4 failure modes. All say the dam should have failed by that failure mode. So which one is it? Or which combination of the 4 is it? We didn't know. It was just getting more interesting. Malpasset Dam had failed in 1959 at an identical failure mode. And the guy that designed it had a PhD, and he was the world's most famous arch dam engineer, Dr. Andre Coyne. It took him almost the entire decade of the 1960s working with a panel of experts to figure out why this dam failed on its first initial filling. And it was uplift pressures, and it was in the schists, and there was a fault. All common elements with St. Francis. So we then went back and looked at the landslide and tried to model that and said, okay, let's go down there where we have wedge B coming out, and right by block 35, let's pull block 35 out and let the water shoot out. Because we had one eyewitness account from Luis Eller's husband that he felt a mist in the canyon, and the mist would travel down the canyon as a density current when you're spilling. That's a big issue with dams. And that's what woke him up. And then he heard the thing coming like a freight train. So when we analyze that, sure enough, the whole thing comes down. What we learn is we develop really high pore pressures in here because the water can't get out. The water is basically caught in here like lithium grease. And it greases this whole thing, and the mountain just comes down on top of it. And guess what? It's 70 feet thick. It's the exact thickness that we measured out there after the failure. Isn't that interesting? That's another failure mode. Okay, dead fish in the sabotage theory. Lots of big spill pools, plunge pools, filled with dead fish, and they actually did autopsies of these and found they were killed by turbid outflow. So the fish gills were choked with silt debris. It would have taken about 12,000 pounds of dynamite under 30 feet of water to blow it up. Nothing approaching that ever occurred up in the Owens Valley. They only used a couple sticks here and there, dynamite. They never had 12,000 pounds of it. And to get it underwater and so on and so forth. And if you had detonated 12,000 pounds of TNT, you'd see it on the seismographs. And they looked at all the seismographs in the San Gabriel Mountains and the Tehachapi. They didn't see anything. That would have been, 12,000 pounds would have been like a magnitude 4 event. So it should pick up real easily. They pick up the quarry blasts routinely all over Southern California. Every single quarry in Southern California gets recorded on a seismograph. I couldn't use the dam site for back analysis of the outbreak flood. A hydrograph is is the relation of flow with time. So it's going to pick up, reach a peak flow, and then it's going to have a tail that goes down. The area under the hydrograph is the volume of water lost out of the reservoir. So I had to go to another site, because here the cross-section changed every second, because you had more and more parts of the dam falling down and being moved downstream. So you got to go downstream where you have some data. So I got the right slides now. We missed a lot of slides. We know that the reservoir drained by 1:09 a.m. That's what the reservoir floor looked like the next morning. And we know that was 36,162 acre-feet of water. And we knew that the power line went down at 11:57.5, and exactly 5 minutes later, Powerhouse 2 went offline 7,300 and some feet downstream. So we know those things. And then we go out there and we use terrestrial photogrammetry to figure out where the high water lines were and the high water marks. And that's where I go out and I take a stereo pair with the old photograph with one taken today, and then I can do different offsets to make different measurements at different distances from me. That's an old naval attaché spy trick. So say you're in Shanghai harbor and you're across the harbor from some ship. You take a picture here, you look on a map to see how far away it is, then you calculate a 1/2 degree variance, and you step over here, take another picture of the same thing. You got a stereo pair for that distance. So you take groups of stereo pairs depending on what you're trying to measure. For block 16, that's pretty close to me. For the high water line on the road over there, that's much farther from me. And then the dam's way out in the distance behind me. So that's how I get the water line depths from the old pictures. So we go to Powerhouse 2, and we got a nice bedrock cross-section, and we know E.H. Thomas, the surge chamber attendant, came down, and he noted where the high water had been at 12:15 a.m., and he went another 20 feet. So the water had arrived at 12:02.5, taken the powerhouse out. It rose up to about 110 feet, and then it dropped 20 feet by 12:15. Wow. I got some data, and I can put that into the computer program, and actually we got a very, very clean hydrograph the first time out. That's the only time that's ever happened to me. And here, it's a peak flow of 1.3 million CFS. Up at the dam, it was 1.7 million CFS by backing up the model to the dam site. So that's how we do it, to figure out what the outbreak flood was like. At the time, they estimated 400,000 for the maximum flow. They were way off on that. How did such massive blocks of concrete, some weighing 10,000 tons, move 1/2 mile downstream? When we go out there and we look, there's lots of evidence of hydraulic sorting. As I was talking to the group this morning, you get the real coarse stuff up near the dam. That's 12-inch stuff there with blocks 11, 12, 13, 14. When you get further downstream, you get the silt, the muddy stuff on top of the sands. And you have a lot of, as the low flow goes out, it also takes out a lot of the fine stuff and moves it further downstream. And this actually shows the effective weight of the dam's concrete depending on the percentage of entrained solids. So you have the dry weight of 143 pounds per cubic foot. It was never that heavy, because when you're saturated, you'd be 143 minus 62.4. And then if you had 10%, entrained solids 20 or 30, which is what they had. They had about 30 with the landslide. The effective weight of those blocks is now down around 60 to 65. That's how come they tumbled over and over and got down that far downstream, because they're in a very turbid or muddy outflow. And that was confirmed with the victims' bodies being filled with silt, their stomachs and esophagus as well. Now, the other thing was when the Ray Sylvie family went by about 8:30 p.m., they're going up to Powerhouse 1, where he came on shift later that night. And when he gets about 100 feet past the dam, you notice the road. The road's about 7-8 feet above the dam crest. And it's in 100% in cut. So it's in rock, it's in bedrock. And he hit a scarp, which looked like that, 12 inches high. And the car couldn't go any further. He had to get out of the car and dig off the scarp. Now, when I first read that in the second volume, which Wendy kindly found and sent to me, Wendy Larson Cleaves over here years ago, that's one of my most treasured possessions, is the 1973 version of Outland. I find out this story, and I just come off my seat. I'm going, 12 inches? That means the whole mountain moved 12 inches next to a concrete dam, 100 feet away. That's not good. That's like driving the wrong way on the interstate. That's not good. Something's going on there. There's some big movements going on, big adjustments. And so this is the likely failure sequence that developed. Something's going on down there near block 35. We got the mountain starting to move. We know the dam has been tilting for the last 3 hours in cantilever action, and things start coming apart. And 45 minutes before the failure, somebody goes by the dam and they see a light on down at the base of the dam. There's no lights on the dam. Somebody's down there with a flashlight or a lantern looking at something. Probably Tony Harnisch-Fager, probably with his wife, Leona Johnson. We don't know. That's why we like to find the Leona Johnson file. And so she's found allegedly fully clothed, wedged between two blocks near the base of the structure. That's a fantastic story. I mean, I hope we can corroborate it. Bodies, people who are living quarter-mile downstream of a gigantic flood don't usually found upstream of where they were sleeping. That's like me flying up to 30,000 feet right now just off a fart or something. That just doesn't happen, okay? You know, I'm not going to go that high. So you can't go upstream against a huge 1.7 million CFS flow. So it's hard to believe her body could have even been preserved up in that area, given the kind of forces we're talking about. But that's the story that's been passed down. I'm trying to get that one nailed down before I write the book. So I have an east abutment landslide at the beginning of the failure sequence. I didn't come up with that, Charles Outland did. I just drew it first. He came up with the idea. And when I looked at it, I went, that's exactly what had to happen because of all the chatter marks across 2, 3, 4 and block 1, which you're going to see in a minute. So this big slide comes down and it weighs 10 times more than the dam weighs. Doesn't have any trouble moving the dam around. And there's a sea wave that goes across to the west shore and bounces back to the east shore, shown right here. And we're well above the high water line. And we got wet water and a muddy area here on San Francisco Canyon Road. There's what a county road looks like back in 1928. So no low clearance sports cars around here. Okay. So that is followed by block 7, which is the leftmost block, top of the left abutment, slides down, as you see there, in behind block 5, and you can see how it cleaves off the downstream face of the dam to a depth of about 18 or 20 feet. So it takes the 18 or 20 feet off the dam like you see there. It's coming across and chopping those blocks off. And that's a huge forces going on in terms of the shear force. And at the end of it all, block 5 sitting there, and 40 feet above the channel, you have all the schist detritus sitting over it. Now, there's no way the thing fails on the right abutment in the conglomerate and puts a bunch of schist up on top of this block 40 feet higher over there. This doesn't work that way. All these rocks are dumb. They obey gravity, okay? And they're just going to go where gravity takes them. You can see a person there for scale. And that schist is still sitting in there, and they're big blocks. They're real angular. They haven't been tumbled in water for any short distance or anything. They're just right out of the slide. And there's again showing the schist detritus caught on the steps. And this block 6 is a little piece of 5 that fell out a couple afterwards. And there's again people for scale. The base of block 1, which is cleaved off.
That's a spillway, isn't it?
Well, the whole downstream face is a spillway.
Right, but I mean the rounded.
Oh yeah, that's a spillway slit. Yes, that's a spillway slit. That's correct. Yeah, he's talking about right here. That's one of the spillway slits there and right here. And then that's the solid section where they had the outlet works. And then there's other slits over. Actually, that's the end of the spillway slits in block 5. I'm sorry, that's the end of them. That's the last 2 on the left side. Okay, so here's something really interesting. If you look at where the cleaving occurred, it goes down and then it comes up. But then block 5, which did the cleavage, is dropped down about 35 feet. See, that block originally was way up there, and then when it broke on the right abutment, later in the failure stage, it sluiced out a bunch of material and this thing slid down to its final resting place. So that's the gap. You have to put the pieces back to where it was. And again, the governor's commission didn't catch any of this kind of stuff. This is details. And so if we look at block 7, that's the uppermost left abutment block. It slides in behind block 5. Well, what happened, block 5 was higher. It cleaved off, came down, came up on the right abutment, and then fails back down against block 7, which has it wedged in there real nice. So here's what's going on. Block 5 flows down on the landslide, comes around, comes up because of the opposing valley wall, and then when that fails later, where the small blue arrows are, it falls back down. Meanwhile, the landslide dam's being excavated in about 5 minutes. So 700,000 cubic yards of silt, of schist, it's not silt, it's rock, is getting blown out of there in a 5-minute period, creating a very, very turbid outflow that carries these big blocks downstream, and it's carving out a big hole underneath the dam. And after the failure is over with, they actually surveyed block 1 because they had a theodolite station and they had benchmarks in the dam. They had a benchmark in block 1. And they determined very precisely that there was clockwise rotation of 0.7 feet, or 8.4 inches clockwise, which attests to the big hole that was dug on that side of it. That's an enormous block to move that much, by the way. So here's what I think happened. The lake drained rapidly, took out the slide debris. That took 5 minutes. After that, it started eating out the base, underneath the base of the main section of the dam, to a depth of about 40 feet. That's a big hole. And the combined flood wave at this point, when the right side goes out with the left side at that water level, is about 1.7 million CFS, cubic feet per second. We can actually see on the right abutment, where it supposedly happened first, this guy is standing on the high water mark. Now, look up above him. That's the right abutment thrust block. The water was within 20 inches of the top of that block. That's where the water level was when they started. So you can see the water has dropped down almost 70 feet to get to where this guy was. So that lake had drained down from almost 70 feet down before the right side broke. And you see that in other pictures. Here we are on the right abutment. There's the right abutment thrust block, right? Right there, that's the right abutment thrust block. And you can see we're standing here and all the weeds and everything's still there. In fact, the high water mark is way down here below the word access road. That's the high water mark. And the water was right up there, right at the gunnels. Right there is where they started. So that is a big drop in water before the right abutment even goes. So what happened with the Governor's Commission? They're not forensic engineers. They're designers. And they're all very important men. They don't have a lot of time. They wanted to get this thing done. They got it done. They didn't do a very thorough job. Because that's all evidence you could see with the naked eye. So if we look here, every picture we look at, you can see the erosion begins way below the access road, which is about 70 feet down, 75 feet down in that particular picture. That's about 2/3 of the lake being drained by the time the right abutment side fails. At the very end of the failure sequence, when there's only about 16 feet of water in the lake, the left half of the dam, of the main dam, topples backward at an angle of 54 degrees, and you get blocks 2, 3, and 4. And that's because of the big hole excavated underneath it where the landslide dam came out. And that's what it looked like the morning after when they got out there and got to see it in the first sunlight, first daylight. That's what it looked like. And this is the picture that Charles Outland looked at, and he saw the cleave marks, chatter marks on the downstream face, and he said, block 5, 6, 7 had to be carried across in the landslide, and it chattered away that and came around, and you know, he had it all right. It's exactly right. Pretty good job of forensics. Okay, now we get behind those toppled blocks. Look what we see. Horizontal lines. What are those? Well, those are pieces of silt. This thing fell backward into the sediment that's in the reservoir, and you got about 17 feet of water. It's real turbid, and so that turbidity is recorded on those blocks. And the lift heights right here, you see those lines right there? Those are 5 feet apart. They're 5-foot forms. So using those, I can easily get this height is 16 feet right there. So it's very, very late in the failure sequence that this enormous series of blocks breaks over and topples, and it's just uncanny that this thing just cleaves off like this. Well, the reason this cleaves off is because of those pillows I showed you earlier that are real low strength, and they're undulating, and don't have any tensile strength, because the latence layer is like a layer of grease sitting there. They should have jetted that off. So the blocks break in tension when it falls over, and they're very big and angular and nasty looking. As you can see them there, they're huge blocks. It's half the dam, half the main dam, basically. So that's the final configuration. You can see the power lines, you can see the high water line. The story it tells is a left abutment failure first. Mulholland gets tried in a coroner's inquest, and Asa, how did John say it, Keyes? Keyes. He wants to become governor, and he wants to take Mulholland on and sue him or charge him with negligence for the deaths of all these people. And Mulholland gets up on the stand and says, you know, he only envies those that were killed. Don't blame anyone else, just fists fasten it on me. There was an error in human judgment. I was the human. And that turns out to be right. And that was a pretty... Now, if we look at the coroner's inquest, I was very impressed at the questions they asked. I was more impressed by the report they wrote afterwards. These men were not paid a nickel. None of them had any tie to the Department of Water and Power. They were eminent engineers. 3 of them were very eminent structural engineers. One was a mining engineer. They were learned men. They write down, a sound policy of public safety and business and engineering judgment demands that the construction and operation of a great dam should never be left to the sole judgment of one man, no matter how eminent, without check by independent expert authority. For no one is free from error, and checking by independent experts will eliminate the effect of human error and ensure safety. That has been quoted across America thousands of times since. And some men in Los Angeles, when it was a tiny place compared to what it is today, wrote that. There's an incredible amount of wisdom in that statement. That's exactly right. Okay, so who actually designed the dam? It was, quote, laid out by the Bureau of Waterworks and Supply Office Engineer Edgar A. Bailey, somebody I've studied in great detail. I even have his book collection, which I got lucky to find in a used bookstore one day on Wilshire. Yeah. My wife didn't think it was lucky because we missed a couple house payments. Everybody has their weaknesses. Mine's not prostitutes, it's books. There's no hard evidence was ever found that any rock cores or tests of the foundation rock were actually made by the Bureau of Waterworks and Supply. Mulholland got up there 7 times, talked about the cores. Yeah, we did cores. Yeah, we tested them. We better get those over. Billy, get those cores and get them over here. They're never produced. And this goes on for 3.5 weeks. And it's the same thing every time. There weren't any cores. Now, the cores may have been destroyed. He said they were stored out there and they were lost in the flood. I might give him that. But I know Mulholland, and I know if he had tested them, the records would have been there, because everything else that they did was there. The records were there. They were never produced. The design appears to have been based on examples in 3 books: Smith's Construction of Masonry Dams, Fowler's Water Supply Engineering, and Wegman's Design and Construction of Dams, all of which get mentioned in the coroner's inquest. I have copies of all those books. I looked at them, and nobody claimed credit for designing the structure. When Bailey is put on the stand, and this is the acid test in the whole 818 pages, and they say, Mr. Bailey, did you do the design? Did you design the St. Francis Dam? And he goes, I did not design the St. Francis Dam. Pretty definite. But everybody else says that he did. What he did is, he said, I laid it out according to Mr. Mulholland's direction. I laid it out. That means he took the design for Weed Canyon, Mulholland Dam, and he made it fit the site in San Francisco Canyon. And the only calculations they did was to figure out how much concrete they were going to need. That was it. There were no stability calculations done. But they were following those designs in those books, which were industry standards. And that's what a lot of people did. That's how engineering was done in the 1920s. And that's why the Governor's Board of Inquiry and the other boards of inquiry didn't fault him, because they knew that. But yeah, it was pretty much the way other people did things, if you believe their cross-section. That's the drawing on their original application, April 16, 1924. It did not get built that way. That backward batter's not there, and those steps don't go down all the way. But that's where they got the drawing that they gave to the Governor's Commission. But it's not in line with what all the construction photos show. Okay, fixing blame. The coroner's inquest comes out. They blame the dam disaster on the foundation, and Mulholland took the blame for the mistakes. And that's the end of Asa Key's political career. He ends up, by the way, going to San Quentin and spending the rest of his career there. He dies before Mulholland does. He's half his age. So when the guy admits to being the fall guy, that's the end of your case. You don't get to take it to the jury. You don't get to be on the cover of the LA Times and the Herald Examiner every day, because the guy just said, I am to blame, blame me. Cut it short. It gets out of the papers day after that. It's gone. It just vanishes. Okay, what were the design deficiencies? A lot of people have said, I go around defending Mulholland and saying he didn't do anything wrong. Those people don't come to my lectures. But they're out there. They're writing books. They're making money. Okay? I've never said there weren't huge design deficiencies with St. Francis Dam to any crowd anywhere. The dam was unknowingly built against a paleo-landslide. Well, you're going to find out that happened in more than one instance. This is just one out of about 157 or so that happened in the United States. The impacts of hydraulic uplift were not incorporated into stability calculations because no such calculations appear to have been made. That's my current stance on it. I do not think there were any calculations made. Does that mean they were lying about that? Yeah, that's what it means. Hydraulic uplift was not relieved on the sloping abutments. Well, that's a deficiency, but it was a common problem up into the 1960s. They certainly weren't the only ones that did that. No grout curtain, shallow shear keyways. I would fault them for no grout curtain. That had been done at Elephant Butte, 1915. They could have done it here. They should have done it. Cement heat of hydration effects were ignored. That's another one that's hard to forgive given the size of the structure and how fast it was built. Low strength lattice layer between successive lifts was not jetted off. That created low tensile strength horizons. That was not an uncommon problem in all the dams in Southern California made out of concrete prior to 1935 or so. Aggregate separation using trough placement was also a common 1920s problem. Design deficiencies number 2, the upstream heel was not battered like they showed on the drawing. The dam, that was because the dam didn't go down that deep, as they showed on the drawing, by the way. The dam was heightened 20 feet without increasing the base width. That was a serious oversight. Downstream face was chopped off at elevation 1650, giving a thinner cross section than actually required to overcome uplift of the upstream toe. The upstream toe obviously went into uplift because it had a crack. Absence of grounded contraction joints with water stops, that became fairly uniform practice with Hoover Dam a decade later. Plugging the dam's expansion cracks with oakum on the downstream face was the worst thing they could have done to destabilize the dam. That occurred in January, February 1928. I had pictures of that. You missed seeing them because I had the wrong lecture up here. I apologize for that. That occurred on the Facebook page this year. Picture of the grouting operation, little grout pipes, taken in January 1928. I went, wow, do I like Facebook? I might miss a lot of things, but I don't miss any of those postings. Gypsiferous Vasquez conglomerate was subject to slaking under submersion. Not great stuff to build a dam on. If you build a dam on something like that, you have to have a lot of grouting and a lot of drains. No instruments placed in the dam structure to monitor actual performance. By the way, Baldwin Hills was the most instrumented off-stream reservoir in the country when it was put in. Instrumentation's never going to save a flawed design. Okay? You have to do something with the instrumentation, and you have to have authority to do something about it when you read the instruments. Okay. Conclusion number 1. I want to give you a quote from Mencken. For every complex problem, there is a solution that is simple, neat, and wrong. That's me on St. Francis Dam. I was wrong for a long time. And I'm just here to tell you. That's why I want to tell you. That's the message I'm going to tell you. I looked at a lot of different things, but I looked at them in a vacuum instead of looking at them from a systems engineering point of view, which is you got to look at everything, not just your own specialty. You got to look at everything. And it's the combination of all those things that come together in a deadly way that create catastrophic failures. A calculated factor of safety, less than 1, does not in itself mean the structure failed via that mechanism. I did that on Teton Dam for my PhD. And we got a factor of safety less than 1, and we said it's hydraulic fracturing. That's what made the dam fail. And we published lots of papers and all this. And I look back on that now and I just go, wow, dumb kids. We didn't analyze other failure modes because that first one was so terrible, we just assumed that's how it failed. I don't know that any dam failure I've ever worked on was just one single thing. I don't believe that anymore. It's more complicated than that generally. You have to have redundant systems that are robust to overcome having one thing break. It's like designing an airplane to go through combat. If there's one place you can put one bullet in, it brings the plane down, that's not very robust. You know, it has to be able to have some major system failure and not come out of the air because the consequences are so grave. Various failure mechanisms compete with one another simultaneously. That's what was going on here. We had the landslide, we had the pore pressure in the internal cracks of the dam. We had all these things going on simultaneously. All manner of failure mechanisms should be evaluated without prejudice, and that's difficult to do, for we're all prejudiced by our life experiences. I never saw the big, huge landslide on the left abutment till I read Bailey Willis's article. June 28, 1928 issue of Western Construction News, a trade journal. And when I looked at it, I said, how could I go out there so many years with so many credentials and miss this? I missed it because I wasn't looking for it. That's why I missed it. You're going to miss anything you're not looking for and that you haven't been exposed to previously in your professional career or professional training. That's why the inclusion of a geologist on something doesn't insulate you from geologic disaster, because you're going to be limited to that geologist's experiences, and it might not be in all the things you need. You'll see that next. So that's what I just told you. We're only going to see those features or structures that we're looking for. And we need to have in mind what we're seeking, realizing we're not going to see it if we don't have experience with it. I used to think there were these mega landslides coming out of Drinkwater Canyon. That's in the Dibley thing in 1997, coming down. And Professor Perry Elig told me, no, I don't think that's what's going on out there. And he was the expert in the Pelona schist. And so I wrote to him, and I called him, and I tried to get out there in San Francisco County, and I never, we're always too busy, couldn't get it. Finally, I got discouraged, and I sent him a $100 bill, and he called me. Naked women, $100 bills, they both work. Okay, so I got down here, I spent 2 days with him out in the field, and he talked me out of that whole scheme. I went out and showed him a lot of things he didn't know about, but in the very end, that's an old erosional surface running off toward the San Fernando Valley before the Santa Susana thrust came up. And it looks like the headscarp of a giant mega slide complex, but it's not. So I changed my mind on that one. I retracted. That slowed me down on writing the book. Okay, we're almost done. Engineering geology is very subjective, and it all gets down to the geologist's experience. Consider the fact we now know there are 153 dams in the United States which were unknowingly built against ancient landslides. Okay, here's one place where I'm gonna toot my own horn. Because of my work on St. Francis Dam, getting national attention and some national award from National Research Council, the Corps of Engineers and the Bureau of Reclamation hired the U.S. Geological Survey to look at all the dams in the United States and see if any other dams were similarly built against paleo bedrock landslides. I didn't get any of that work, but a bunch of other people did, and they found 153 dams. I'm more proud of that than any other contribution I've made to my profession, because that wouldn't have happened if I hadn't written about St. Francis Dam. And that was a $2.9 million study that I missed out on. Okay, last slide. Bill Mulholland had weak points in his character, like any of us. I think his biggest one was his thirst for thriftiness, because I had a lot of clients like him. And, but that was the same thriftiness that allowed him to build a municipal infrastructure for Los Angeles at rock bottom prices. No question. You compare LA to San Francisco, you get your water for about 1/10 the price they got theirs with Hetch Hetchy, okay? And he had an enormous capacity for innovation. The story I don't want to let you go without telling you is Elizabeth Lake Tunnel cave-in across the San Andreas. It caved in. They had 6, 7 miners on the other side, 300 some feet away. They couldn't dig them out in time to get them before they asphyxiate. Mulholland went in there, assessed the operation, and he said, okay, go get me a bunch of 2-inch diameter pipe and bring it here. And they brought all this pipe in, and they went up to the crown of the tunnel, and they screwed on a cap and said, unscrew cap, scratched on it, and they started pounding this thing through the cave-in, all 300 feet on a slight decline. And when they got to the other end, they could tell there was no more, there was less, these guys pounded on it from the other end, so they knew they got through. They opened it up, they could talk to them. Then they said, get your canteens out, we're gonna pour water to you. And they started pouring water. Then he got a bunch of hard-boiled eggs, and he started shooting hard-boiled eggs to them to feed them. And then he started pumping air to them, and they saved all of them. They don't teach you that kind of stuff in college. You got to think on your feet to do something like that. The man was pretty brilliant when it came to solving problems. And he appreciated geology much more than most of his colleagues of his era. He was the first civil engineer to recognize the threat of the San Andreas Fault posed to the municipal infrastructure of Los Angeles. He was way ahead of his time on that one. He had the depth of character to accept responsibility for the shortcomings in the dam's design. He didn't know why it failed. He was surprised. He was befuddled by it. Heck, he had copied these designs in Wegman and Turnio and all these famous books. Why didn't it work? Very few people at the time really comprehended. They didn't want to really know why it failed. They wanted to get it swept under the rug and get on with the Boulder Canyon project. And that was asserted in 1978 during the 50th anniversary when they went and talked to Charles Outland. And years later, I get on the Hoover Dam board. I start studying Hoover Dam. I've written all kinds of stuff about it. He was right on target once again. Charles Outland, what a man. Don't honor me, honor him. He did a great job as a amateur historian. Did a great job. All right, that's all I have. Thanks.
I imagine there's a question or two, if you would be so kind.
I'll take questions, sure. Yes, ma'am.
Yes, just wondering, in all your readings, did any of the people that were working in the camps at the time notice things, say anything to the people?
Well,
or were they, what type of people were in the camps?
Most of them were appreciative of getting work. There were a whole bunch of them that were brought through to the coroner's inquest, and who said, I saw water squirting out, I saw substandard, workmanship, blah, blah. None of it amounted to anything. These guys were bright enough to see through it, and sometimes they didn't understand that, all dams leak. I mean, Glen Canyon Dam, we have, 8,300 gallons on the left abutment per minute, and about 5,900 per minute on the right abutment. But the lake's 27 million acre feet, so that's a tiny trickle. But if you get inside the dam and see the cascading water, it's a lot of water.
Why did Van Norman take some responsibility? Was he also, okay the whole thing?
No, Van Norman was actually on loan at this time to the LA Sanitation District. And he was heading up the sanitary outfall, first when they were building off the shore. So he came out here because he was Bill Mulholland's favored protege, and he was grooming him to take his job, which he did.
Which he did.
Yeah, until 1944. So from January 29 to 1944, when Morris came on from Stanford, Harvey Van Norman was a chief engineer and general manager at DWP. Yes, sir.
When I was up at the dam, I noticed that the concrete seemed to have large rocks in it.
Oh, yeah.
I thought, gee, this doesn't look right to me. It seems like you should have more concrete and less rocks or smaller rocks. Was that a factor at all in the dam?
No, I've done a lot of forensic work on the concrete. There's problems with the concrete, but the concrete's there to take compression. And the strength's not the issue, purely. Yeah, it's as strong as the aggregate. And you look at Hoover Dam, they got rocks up to 9 inches, Hoover Dam. So those rocks they have there are not a big problem. Yes, ma'am.
Are there any questions that you wish you could have answered?
Oh, yeah.
Of
Oh, yeah.
particular people that you wish were still around, that one that's just like, what are those?
Well, the one about Leona Johnson's body is a big one. I'm sure I could come up with more. that one's a fan. That one would really explain what happened to Tony Arnish-Fager, and of course his son Connor, was 6 years old. They were the first victims of the thing, and your heart just has to go out to them because he called the boss to come out there 12 hours beforehand and got told, hey, everything's all right. I'm sure Mulholland felt tremendous remorse about that. But there's a lot of things. I see things on that are posted all the time that are always surprising me. So, Ann, if you're interested, get on the on the Facebook page. It's really interesting. We've got some interesting stuff. Yes, ma'am.
If all the drawings, the plans show a wider base and a toe, at what point were they taken off, and who made that decision? Who
Well,
did that?
Yeah, we don't know. That's one of those things that's, all I have is those drawings. And I know that the drawing they gave to the governor's commission was based on that April 1924 drawing. So that's what they showed the federal government. It was the forerunner of FERC, Federal Energy Regulatory Commission. It was called something else at that time. So that was what they put on the application. That's not what they built. And then when you go back and you look at their concept drawings, they did the original stability calcs on it, had a chopped toe. So I don't know. That's a mystery still. But I know the one they gave the Governor's Commission was not correct. And Outland, again, I'm riding Outland's coattails on that. And I really want to point that out for those of you who are amateur historians. You can make a difference. You know, he was around a generation ahead of me, 2 generations ahead of me. So he had a lot of people he interviewed that I would never be able to interview him. But I benefit from his work tremendously. Yes, ma'am.
My grandmother went through that.
Really?
She was one of the people that ran for her life.
Wow.
Yeah, and her whole family.
Did her family survive?
Yes.
Okay. Wow.
Where they live?
Where they live.
Wow.
Mulholland?
What was her name?
Yeah, these guys.
What was her name?
Wow.
In Navarro family.
Yes,
Thank you.
go ahead.
Thanks for-
How are you gonna find out about Leona, Johnson?
I'm going to give that one, I passed that lateral to Ann Stansel
I'll see
today.
what's in the claim file.
Yeah. And then,
But I mean, her body clothed at the dam, that's gonna be.
That's what they
never
say.
in the claim file?
It could be documented in the
Okay.
claim file,
Yeah.
yes. But I believe that that story comes from the 50th anniversary.
Right.
that Don Ray interviewed someone.
Right.
that's,
Right.
Spanhauer,
Right.
said that he was at.
Spanhauer, yeah.
Well, it's kind of hearsay.
yeah, that's why I haven't put it in the book.
But what would that prove? I mean, if.
That would prove that she was up at the dam with Tony looking at something with a lantern. So there was something going on that brought him to go up there like a high pressure orifice spray coming out at the base of 35. Yes, sir.
Michael Connolly will have Harry Bosch solve that problem. You mentioned his thriftiness, you have it up there.
Yeah.
He was given a budget of $23 million to build the aqueduct. He built it for $23 million,
Yeah.
and there was none of today's cost
Right.
overruns.
Right.
He should get some credit for that.
Oh yeah, he does. He does with my writings. He
My
does.
main question to you is, your major article came out 20 years ago.
Right.
You're working on a book. You're re-evaluating your earlier conclusions then,
Right.
and you've
Right.
changed your mind on stuff.
Yeah, I always do that. Whenever I testify in any trial, I always say I reserve the right to change my opinion at any time based on new, credible information coming to
This is
me.
an article, and it's out there, it's in St. Francis Dam Observed book, as well as in the magazine, and I know you published a couple of other places.
Right.
So this could create some sloppy research from people who
Right.
take it for what it was
Right.
back then.
Yeah, there's a lot of people that write a lot of stuff and they don't even contact me. And they take what I've written and they misinterpret it, or they don't talk to me to see that I no longer hold to that as a tenet. But I would agree with you about Mulholland's ability to bring difficult projects in on time and on budget was phenomenal. It's the only word I can use, phenomenal. And he was also a pioneer in recognizing seismic hazard, seismic risk issues. Yes, Frank?
Back to Harnisberger.
Yeah,
Now, he was, if I remember correctly, he was a guard on the aqueduct.
Right.
For Mulholland.
right.
So he was working for Mulholland for just under 15 years. What expertise was given, did he have to be promoted to dam keeper?
Well, dam keeper is just there to look for, at obvious things. He's not an engineer, but he would be expected to call them if he saw something that was unusual, a change. And so the change that day was the cloudiness, the turbidity of the water. And he was probably told, look for, if a leak springs up out of the ground and there's muddy water, you'd be real concerned. And so that's the translation that got to headquarters, but when they went out there, it was if you followed the water all the way up to its source, the source was clear at the base of the dike section, and it was just getting cloudy where it was going over the side cast fill for the new road.
Well, I'm clear on all the story there, but I'm just wondering what the relationship with Harnisberger and Mulholland were. I mean, how
Well, he was way down here from him. I mean, he was the dam keeper. Mulholland says by his own testimony that he toured all of his dams on a 3-week rotation. So he went around to all of them and checked on all of them at least once every 3 weeks, which is very credible. I mean, we didn't even dream about doing something like that today with a chief engineer, general manager of a big, huge utility like that. That's pretty amazing. He found the time to do that. Yes, ma'am.
My husband's uncle worked at the dam, and he was lost, and his body was never recovered. And since we saw about the event today and planned to be here, I looked through some old photographs, and I have one, and I'd like you to look at it. It's not identified.
Oh, that's Powerhouse 2 after the failure. That's the
where it
Francis
was.
turbine, yeah. That's Powerhouse 2. Look at the collapsed walls. Right. That's one of the.
His name was Basil Ross, and he was one of the 3 men on duty at the time.
Oh, okay. That's why his body wasn't found. Okay. Okay. He was in the powerhouse. Okay. Right. Yeah. That. Those generators were put back into commission. That was another Mulholland. I mean, that's amazing. He was able to do that.
Same year that we're
Yeah.
running in November.
Same year. So they had to go in there and clean these things off with hydraulic hoses and everything, and then dry everything off. And that was no small feat to get the silt out of it. The silt's very, very fine, and it's very sugary, and it's micaceous. So they did an incredible recoup job on that.
One was turning, one wasn't. The one wasn't
Yeah,
turning.
right.
All they had to do was clean it.
Right. Right. Well, one of the turbines was running at the time of the flood, and one was not. The one that was not turning was real easy to clean. The one that was turning was, of course, very hard. Yes, sir.
Have you found solid evidence that there was no sabotage?
Yes. Yeah. I worked on that a lot in my Navy job because I worked in the joint targeting group on dams, bridges, and tunnels. So I studied the Ruhr dams raid in great detail. Even went over to Europe, got the Germans' forensic work on it, which included seismograph recordings that they took, at their learned institutions like the University of Göttingen. And so I have a real good idea for how much explosive energy it would take. And it definitely would register on a seismograph. Every quarry blast in Southern California registers on the seismographs. Every Tom, Dick, and Harry quarry in Southern California. So if they're blowing off a box of dynamite, we're going to pick it up. It's the most dense seismograph array in the country at that time.
Unless they were clever enough to start the avalanche.
Well, did the avalanche show up on site?
No, they didn't. Yeah.
Maybe Ann can answer this too. There are stories that bodies were found as far as San Diego.
Right.
Is that true? Is there evidence of that? And what is
No,
it?
there's no evidence of
So-
that actually in the claims files, but there's a beach along Montalvo that has the same name, Silver Strand. There's one in San Diego, and I think those 2 were conflated.
Okay. That's interesting.
So those Mexican border businesses
Sure.
probably forget.
Sure.
No, yeah, there's no evidence to support that.
Okay. Yes.
I swear I wrote down somewhere in my 11 pages of notes the word drought this morning. What were the weather conditions? Was there an ongoing drought? Had it been an El Nino year? Just curious about what weather conditions might have done to already make the Kelowna system unstable.
Well, there was.
Or prone to
Yeah.
migration better.
Yeah. There was a drought in Southern California, and so there was more water demand. And that drought actually stretched to the Sierra, so there wasn't as much snowpack. And so that's the combination of those 2 things that got them.
Kind of the demand. I was just wondering
Right.
if there might have been an effect on the
And the
local
demand was going up every. No, I haven't seen anything. I don't recall anything of that era. The first big landslide I know of in Los Angeles is Point Furman in 1925.
And it's still moving,
Yeah, it's still moving.
as
Yeah.
Harry would have told you.
Yes. Yes.
The question is, with Mulholland, since he worked for the Department of Water and Power, was he a wealthy man? What makes his net worth, let's say?
He didn't even cash a lot of his checks. When he retired, they found checks in his desk that he didn't cash because he was a consultant to East Bay Municipal Utility District and Tacoma Power and Light, a lot of other agencies used him as a consultant. And he felt that he shouldn't profit from experience he had gotten on the public till in Los Angeles, because he's a progressive.
That's common.
Yeah.
But
So-
was he a wealthy man?
I don't know. He couldn't have been too poor. So I don't know.
He was not happy about the land speculators in the
Yeah.
Santa Clara Valley.
Yeah.
Yeah, he's
Very much
my
unhappy.
kind of guy. in that
Yeah,
regard.
yeah. Yes,
Yeah,
ma'am.
My aunt came up here, my dad's sister, in 1928, a month after
Mhm.
the dam, and the pictures that I have, which are on the website, it was very windy. I have photos of the Edison trucks being demolished that she took, and trees that are mangled, and
Right,
her
right.
friends standing in front of it, their dresses are blowing up.
Right.
You know, so.
That's pretty common after floods because of all the silt beds, and their silt's not stabilized
So it's
by
really
vegetation,
windy in April.
and it doesn't rain for, if it doesn't rain for like 10 days, you're gonna have lots of silt is very, very fine particle, they're like little peas, and it creates big dust problems. That's why like Owens Lake, when you dry it, you get all this dust comes off it, and now the dry lake's out in the Harvey. So that's part of that problem. But the silt is that dust following, several months following a flood is a real common health problem with people doing work, construction workers.
Yeah, one more on what the gentleman touched on Mulholland. Between 1913, when the water came to LA, and drought systems during the early 20s, I found an article that Mulholland had purchased a home out in Soledad Mint Canyon.
Oh, really?
And there he did all kinds of experiments on drought-resistant plants and grasses and stuff like that.
Huh.
We found the ruins out there. It's up in Scherzinger Lane.
Wow.
And so I was wondering if you knew anything
Nope.
about this, or Mr. Hoffman knows something.
I
about
never
it.
heard of that.
But I found this in one of the articles. But the ruins are out there, and we looked at it. And it's a huge house. It was a
Wow.
huge home.
I didn't know
think
that.
it went into, in the 30s, it changed hands and just.
Huh. Yeah.
The family had a 700-acre orchard in Chatsworth,
Yeah.
and it was in family hands down to Catherine's death.
Right.
I was always curious about that.
Yeah,
I haven't been able to get much depth on it.
Yeah, I don't know. I didn't know that.
I've never heard of that story. If it's true, you might find it in the Northridge archives. You know.
Yeah.
Everything to that.
Catherine's, the book,
I've never heard that.
the book she came out with, there was twice as much in the manuscript, because I was one of the early reviewers. And UC Press told her, you gotta take half of this out. It was 1,200 pages. So that it's mostly on the history of the Mulholland family. And that is with the Catherine Mulholland papers at Cal State Northridge Library. Yeah, which I'd love to get into and read sometime. So, because I have tremendous respect for him. But, I can't explain, some of these things like, that have come up. That's all I can say. All right, do you want to tell?